Hello everyone. Today I'm excited to bring to you another conceptually rich problem from physics for students aspiring for engineering colleges such as the IIT or the MIT, or in general physics enthusiasts who love to revisit interesting problems just to keep their brain ticking. This is Kaushik, your friendly physics tutor, here to help simplify concepts of physics one problem at a time. And before I begin, I'd really like to give a huge shout out again to all of you who watched my previous video and subscribed to my channel. Thanks for your amazing continued support. All right, with that said, let's dive right in. So what you see on the screen is the problem we are trying to solve. And what's given here is that there is a disk of say mass m, which you see on the top, which is on a trolley of the same mass m. And the trolley is resting on the floor initially. However, the disk is connected by a spring to a wall with a spring constant of k. And initially the system is at rest, but then it is displaced, say, towards the right, where there is a compression to the spring and the whole thing is released, which then means that the entire system is now undergoing oscillations. Now, we are asked to assume that there is pure rolling between the disk and the trolley, and there is no friction on the ground. And we are required to find that what's the relation between the acceleration of the disk and the trolley. All right. So now I've just converted this diagram into a simpler one. I think the previous one could be helpful for visual learners. But now let's just break down the problem to components and see how we can solve this. Now here it would be pretty clear that if there are different forces like a spring in the system, then you would want to do a free body diagram and capture the forces acting on both the disk and the trolley, right? Now there will be some forces between the trolley and the disk, and there might be some between the trolley and the ground, which is given here to be 0. So let's just break it down into simpler components, and for each of the component or the part here, let's just draw free body diagrams. So I'm just focusing on the disk at the top first. So let me pick up the white color here and say this is the disk on the top. And this whole thing is, say, assume it's going with an acceleration a1 to the left, right? Because of the spring compression, there would be a force towards the left, and it will make the disk move translationally. However, it is a disk, so it will also rotate, right? So there will be an angular acceleration of alpha, as is given in the question, that it is starting to rotate and we need to find the relation between the accelerations and so on. So if it is a disk and if it rotates about its own axis, then there has to be some force which is giving it that angular acceleration, right? So if you look at this body, first of all, I'll suggest all of you to pause at this stage and really think through all the individual forces. So you might say that, okay, there is a net force which is acting downward, which is mg. Because of the extension or the compression of the spring, there will be a force towards left, which will be equal to k times x, right? And because we are assuming that the angular acceleration of the ball is in a counterclockwise direction, as you saw in the visual, the frictional force has to give that angular acceleration, because there is no other force which can give that around the center, right? Both the weight and the spring force are acting through the center, so it's not going to give any torque, or in other words, angular acceleration. So there has to be a friction force from the trolley onto the disk that is giving it that angular acceleration, right? Any other forces? Let's just pause and see if we are missing something. I think we got the weight, we got the spring, we got the friction force, so we should be good. Now let's start converting this into actual equations. So first of all, in the horizontal direction for this disk, what are the forces? Let us assume all the forces towards left, because we took the acceleration e1 to the left, so it will be simpler. So I would say that the net force on the disk to the left is kx minus f, which equals to mass into its net acceleration, right? So this becomes our one equation that we can leverage. Now, we also know that the torque for the disk is given by I alpha, the moment of inertia times the angular acceleration. And given its, for this particular body, now if it's a uniform cylinder or if it's a disk, all of them have different values of I, which is well known to us already. So we can just take it for this particular problem. If it is a disk, then we are taking it to be mr squared by 2, right? And we can use that over here. Now for different bodies, it'll be different, and we just need to be careful what we are choosing here. Also, we know that the torque for this body is nothing but the force of friction multiplied by the radius of the body. It's not given here. Let's assume it's R. And we now know that the torque, which is force times radius, and again, like I said, there is no other force which can give it a torque because both mg and kx are passing through the center, so it will not result in any torque. So the only force which can give a torque is the friction force, that is given by the force multiplied by distance, which is F times R. And I'm going to say the I is mr squared by 2 times alpha, which means we can just cancel out the R, and it gives us 2 times F equals mr alpha. So that's another equation that we get. So we did the linear motion equation, we did the angular motion equation. Now let's move to the other body, which is the trolley at the bottom, and see what kind of forces that has going on. So let me just draw it super roughly over here. Okay, and then at this point we know that if there is a friction acting because of the trolley on the disk to the left, then the same force of friction is going to act to the left here on the trolley. Sorry, the force on the friction is on the right for the disk, which is giving it the torque, and now that same force is acting towards the left on the trolley. Let's assume this was moving with an acceleration of a2 net towards the left, mass is m. So we now know that for this particular body, net force equals mass into acceleration. So that's one equation. However, at this point, I'm seeing that the variables here are F, A1, A2, and X, right? So we need at least one more equation to be able to solve that. And now is the time to think what else can we think of here which can give some more correlations. For example, one of the conditions here that was given is that we should assume pure rolling of disk on the trolley and a frictionless floor. Because it was a frictionless floor, we know that there was no force at the bottom because of the floor, which we didn't use in the force balance equation. However, we all now know that there is pure rolling between the disk and the trolley. So what that tells us is that there will be some relation between the acceleration of the particle over here at the bottom of the trolley, at the point where it is making contact with the trolley, right? So so in terms of pure rolling, we understand that usually we say that v is equals to r omega when a disk is rolling on the ground. But here what's interesting to note is that this disk is not rolling on the ground. The surface on which it is rolling is in itself in motion, right? So for them to have zero relative motion, right, for the condition of pure rolling to apply, we know that this point, let me just mark it with red, which comes in contact with this point, should have at any given point of time the same acceleration. Otherwise they will be slipping, right? To satisfy that condition, we can say that the net acceleration of this point marked by red on the disk would be what? A1 times A1 minus R alpha, right? This is the angular term. So for this particular point, here the net acceleration would be a1 minus r alpha, and this has to match with a2. If it doesn't matches, then there's going to be a slipping. So that's the important concept to note, that for pure rolling, this condition needs to apply. Now that we have 4 equations over here, and given that we want to find the correlation between a1 and a2, it seems obvious that we need to replace the r alpha term and somehow convert it to a1 and a2 form, right? So what I can start doing here is that I can just write alpha from equation 2 as 2 times f by mr, which is equal to a2, which is using equation 2, right? And I see that the r and r gets cancelled, right? And now I also know that using equation 3, a1 minus 2 by m times f, which is given by ma2, equals to a2. M gets cancelled, which just leaves us with what we exactly need, that a1 is 3 times a2. And this is the relation which we wanted, that the acceleration of the disk is 3 times the acceleration of the trolley. Now, this is an interesting problem, and we can make it even more interesting by putting things like, what happens when there is a spring to the left hand side of the disk as well, or what happens when there are additional forces like friction on the ground. So accordingly, you would see that your force balance equations will keep on getting modified, your torque equations will keep on getting modified, and you'll have to account for all those individual forces. So super interesting, but that's it for this video. Let me know if you want to learn more about something, or if there's a particular topic you'd like to explore, and I'm happy to cover it in the next one. Until then, have a good one, and I'll see you in the next video. Thanks.